Chapter 20, Lesson 5. In this lesson, we'll take a look at some more aspects of redox reactions, and this slide is essentially a review from last time, and what we had presented was the reduction potentials table, which lists chemicals in order of their decreasing reduction potential. In other words, it lists fluorine at the very top because fluorine has a very high reduction potential. Fluorine really wants to get reduced, and that is, it really wants to accept electrons. Now recall that substances that get reduced are called oxidizing agents, which means they oxidize the other chemical with which they are reacting. And so at the top of the reduction potentials table, you have very strong oxidizing agents. At the bottom, lithium has a negative reduction potential, which means it does not want to get reduced. It wants to get oxidized. So lithium is a strong reducing agent. So this table can be looked at also qualitatively, and you can pick a strong oxidizing agent or a strong reducing agent as needed. And the idea here is when you're calculating the overall cell potential, remember what we did is we subtracted the cathode and the anode, and so the bigger the difference between the two, the higher the voltage will be. So we've been looking at the copper half reaction combined with the zinc half reaction, and there you get a voltage of 1.10 because you take the difference essentially of the reduction potential of copper and zinc, and that allows you to get this voltage on which batteries are based. Now we'd like to take a look at some equations that connect the different concepts throughout the chapters. So delta G can actually be very conveniently derived in terms of the cell potential, E naught, that we've been talking about. Remember, this is the voltage of the cell. So the the equation is actually delta G equals negative NFE. We're not going to derive this, we're going to simply state the equation and do some things with it. Now N is defined as the number of moles of electrons transferred, so in the balanced equation, and we'll show you how that is determined. F is a constant called the Faraday constant, after Michael Faraday, very important scientist, and it equals the charge on a mole of electrons, and a mole of electrons is quite a bit of electrons, has this much charge, 96,485 coulombs. Remember, coulomb is the unit of charge. And you can also say that this is 96,485 joules per volt moles, because recall that we said a volt is a joule per coulomb. So here we can rearrange to solve for joule, which means we can derive or define it in terms of volts or in terms of coulombs. So this is going to be important for the sake of canceling out units. And we're going to use this equation to be able to determine the delta G of a system. Now, right away, let's take a quick note. Whenever E is positive, if the cell voltage is positive, this means the reaction will run on its own. And that's why we have a negative sign in front of here. That way, when E is positive, this will give us a negative delta G. Recall that a negative delta G means that it's spontaneous. Essentially what we mean is anytime E is positive, the reaction will run spontaneously. And if the opposite is true, if E is negative, then the reaction will not run spontaneously. So actually, let's apply this equation to a problem. Calculate the standard free energy change for this reaction. So the equation was delta G equals negative NFE. Now E is cathode minus anode, so, or rather the reduction potentials of the cathode minus the anode. So why don't we take a look? We'll have to find out who gets oxidized, who gets reduced. We see that silver goes from a charge of 0 to a charge of +1, so silver gets oxidized. Then the silver will be the anode, and so on the other hand, if you take a look at oxygen, oxygen goes from 0 to A-2. Oxygen actually gets reduced. So we'll have to find the corresponding reduction potentials in the back of the book. So take a look at oxygen's reduction potential. So the cathode then will be the oxygen, and the anode will be the silver. So looking at oxygen, and you have to take a look at oxygen becoming water, you'll see that the reduction potential in the back of the book is 1.23. And minus the silver, now silver has to become silver +1. That's 0.799. And notice right away that oxygen has a higher reduction potential, which means oxygen will get reduced and silver will get oxidized. So subtracting the two, go ahead and do this on your calculator. We should get a value of 0.431, but we can reduce that later on. This is volts. The F is a constant. F is 96,500, and go ahead and take a look at the exact value. 485. Practically, for future references, you could use 96,500. This is usually the rounded version of it, and this would be joules per mole, joules per volt mole. And N is actually the number of moles of electrons transferred. Now what we see is, by looking at silver, we have 4 silvers with a charge of 0, and then we have 4 silvers with a charge of +1. So we see that in total, 4 electrons were transferred. Conversely, you can look at oxygen. You have 2 oxygens here with a charge of 0, and then you have 2 oxygens here with a charge of -2. So again, 4 electrons were transferred. And in order to see this, you'll have to balance the equation, and once you've balanced the equation with the lowest whole number coefficients, you'll get N. So in this case, N is 4 moles. So plugging everything in to solve for delta G, we've got -4 moles of electrons times the Faraday, which is 96,485 joules per volt mole, multiplied by 0.431 volts. What you'll see is that the volts cancel out, the moles cancel out, and what you get is you'll get joules left over. And that is how delta G is expressed. It's in units of energy. So go ahead and multiply these together. -4 multiplied by 96,485 multiplied by 0.431. And you should get yourself -166,340 joules. Now let's go ahead and put this in kilojoules, and for the sake of significant figures, we're really down to probably 2 significant figures. This is an exact number. This will not limit us. This is a constant. It won't limit us. But once we subtract these 2 values, we actually get cut off right here. So 2 sig figs, how about we say 170 kilojoules, or rather -170 kilojoules for delta G, which, recall that if delta G is negative, this process is spontaneous. And since it's spontaneous, the delta G should be negative, and you'll see that when the voltage is positive, delta G is negative. You'll always see that to be the correlation. If the voltage were to be negative, delta G would be positive, and it would have been non-spontaneous. So that is how you connect the spontaneity of it to the voltage. So directly from voltage, we were able to find out how much energy the reaction has to release. Here we care more about voltage because we care about constructing batteries from these reactions, but we can convert it, and we can actually take a look at it in terms of free energy as well. The second equation, an important equation we'll take a look at here, is called the Nernst equation, no doubt named after a famous scientist, Mr. Nernst. There are not too many misses. They come up once in a while, but pretty rarely. But what we're going to do, we're going to derive the Nernst equation, and again, if you don't follow the derivation, that's not as important. But it comes from this equation that we saw in Chapter 19, the free energy under non-standard conditions. And if we substitute delta G for negative NFE from the equation we just looked at and do some rearranging, we'll get to this equation. And then if we collapse our constants, these are all constant. If temperature is 298, which it really is, Kelvin, then we get this final equation. The voltage under non-standard conditions is equal to the voltage under standard conditions minus a constant divided by N, and here will still be moles of electrons, times the log of Q. Remember, this is the reaction quotient, products over reactants. And this was very similar in our Chapter 19 equation. So let's go ahead and let's do a little example problem with this. And the point here is that we can actually construct batteries that are not under standard conditions. And actually, even if you construct a battery under standard conditions, once it starts running, the conditions change. And so you're at non-standard conditions, so you have to be able to use this equation. And here is the reaction. Calculate the EMF, or the voltage, at 298 Kelvin generated by the following cell when the concentrations are given here. So we're going to use these concentrations. And the equation is given to us as well. And so why don't we get into using the equation. The equation that we're going to be using, that we just saw, was E under non-standard conditions equals E naught minus, and that number was 0.0592, divided by N times log of Q. So we'll have to first get the E under non-standard conditions. This would be products, or a cathode minus anode. In this case, we see that our cathode, chromium has, if you analyze chromium here, chromium has a charge of +6, and here chromium has a charge of +3. So chromium is getting reduced. Likewise, iodine has a charge of -1, and it goes to 0, so it gets oxidized. So chromium is our cathode. So because chromium is our cathode, let's go ahead and take a look at the voltage for chromium from the back of the book. And dichromate has a voltage of 1.33. So we got 1.33 volts minus iodine, which is 0.536. So we'll be able to get the voltage. Let's go ahead and compute this. Put this into your calculator to get a good number of significant figures. So we get 0.794 volts. Our N, if you take a look at how many electrons were transferred, it may be easier to look at the iodine. We have 6 I minuses, and then we have 6 I's, so 6 electrons were transferred. So we have 6 moles of electrons. Conversely, you can take a look at each chromium. We have 2 chromiums, each is a +6 charge, so we had a +12 charge total, and then we have 2 +3 chromiums, so we have a +6 charge total. Again, you can see that 6 electrons had been transferred. And then finally, Q is going to be products over reactants. So our products, in this case, are chromium 3+, and this concentration is 1.0 times 10 to the -5th. Now this would be squared. Remember, the coefficients go in the power. And then the other two concentrations are going to be reactants. So we have dichromate is 2.0 multiplied by H plus. H plus has a 14 in front of it. Luckily, H plus is 1.0 molar to the 14th power. Looks like I minus is also in there. I minus is also 1.0. So we got 1.0 times, or to the 6th power, because of this. So notice all we did is we did products divided by reactants. Let's compute this. Nice thing is in the bottom we just have 2, because these to the 14th power is still 1. So we're just dividing 1.0 times 10 to the negative 5th squared divided by 2. So this should give us a value of 5.0 times 10 to the negative 11. So we'll have to use these values here. Let's go and plug all this into our Nernst equation. So we have 0.794 volts times 0.0592 over 6 times log of 5.0 times 10 to the negative 11. So first compute the log, and then we'll do the rest of it. So go ahead and compute the log, plug the number in. The log is negative 10.3. .794 times 0.0592 and divided by 6 gives us 0.007834, which gets multiplied actually by this log, so you can get rid of this equal sign here. These get multiplied together for a total voltage. That's a bit strange. Of negative 0.0806. So we have 2 sig figs, so why don't we do 81? Negative 0.081 volts. Now this is actually a bit strange, but it makes sense. Let's analyze if this idea makes sense, and we do have a voltage that is negative. Now, a negative voltage would mean that the reaction will not occur spontaneously as written. So, which is possible. We can still calculate a voltage for it. However, I'm a bit that's possibly. Make sure we plugged everything in right. No, we did not. This is minus. This is not multiply. This is minus. Let's go ahead and modify that. This would be minus. So we may have to scratch some of this. Yeah, so it looks like we forgot the minus. Go ahead and put that minus in there. This would actually change these values here. Get rid of that dot. Excellent. Do not worry. It's always a good idea to check your answer, and if the answer makes no sense, we modify it. So our numbers here will actually change. Let's go ahead and recalculate these. So we got 0.0592 divided by 6. It's 009867. And then subtract 0.794. I think that's a little better. And add it all together, 0.794. Aha! Now we are much happier with this answer, 0.692 volts. Not only is it positive, But what should happen is the voltage under non-standard conditions should be very close to the voltage, not very close, but comparable to the original voltage. This is the original voltage if we are under complete standard conditions, which means 25 degrees Celsius, 1 molar concentrations, and if we're off, then our voltage should change. And here we see that we've changed, our voltage has gone down, but it should roughly still be in the same range. So we actually we've persevered to the end, and this is should be the answer. Before we wrap this up, we should make a statement that the Nernst equation that we just used implies something very interesting. It says, if you study it well, that you could actually run a battery using the exact same substance in both the compartments. So, for example, here you have nickel, and here you have nickel. Now this guy will serve as the anode, this guy will serve as the cathode, and this sounds strange, but as long as you have different concentrations, the reaction will run, and the reaction will produce a voltage. When the concentrations become equal, that's when the voltage disappears and the reaction stops. So for a cell in which the concentrations are different, based on the Nernst equation, which again is E equals E naught minus 0.0592 over N times log of Q, what happens is this guy, E naught, is 0 because you've got the same substance, cathode minus anode, same number gives you 0, but because this portion right here is not 0, it will give you a voltage still, especially if Q is a tiny number. You'll get a negative because if it's the log of a tiny number is negative, and then you'll end up multiplying two of the negatives together and you get yourself a positive voltage. So positive voltage, and you can actually still get your cell to run with a positive voltage, and that's kind of the idea. Alright, so this will wrap up for us. Actually, right before we wrap up, we think we have one more, here it is, I knew it. I knew we can give you an equation where we can derive K, the equilibrium constant, from this equation. And actually it's quite simple. This is the Nernst equation. The second portion of the Nernst equation, if you recall, has this Q idea, and remember Q is really K except before equilibrium. And once we get to equilibrium, we call it K. And so here is the equation. So if you know, this is the interesting thing, if you know your voltage, you can actually know your equilibrium constant. So you should be leaping for joy because we are connecting all these chemical concepts together into one simple equation. Equilibrium can be derived from voltage, equilibrium can be derived from delta G, and delta G can be derived from E, and so on and so forth. All of these ideas come together in a wonderful coexistence, and these are all related, and you can trust chemistry. So this should, for us, complete lesson 5 of chapter 20.